Well, welcome chemistry scholars to our next video on types of chemical reactions and balancing equations. So there are 5 types of chemical reactions. We talked about the difference between chemical reactions and physical reactions. So chemical reactions are changing what it is. It's a change in the substance or material. And there's these 5: synthesis, decomposition, single displacement. So displacement, you could also use the word replacement. They're synonymous there. Double displacement or double replacement. And combustion. So let's start talking about synthesis. So synthesis is putting things together, joining things into one. So when we think about, remember, the stuff we start with are the reactants, and the stuff that we end with are the products during a chemical reaction. So if we have multiple reactants come together to make one product. So generically we can think of it like this: A plus B equals AB. And graphically we can think of the little cartoon here. We got the little emaciated bird there and the big juicy worm, and the bird eats the worm, and now we got a big fat bird. So it's all together as one. Chemically, a chemical example of this, magnesium reacting with oxygen. We saw this happen before, and it makes magnesium oxide. Remember, it got heavier because it pulled oxygen out of the air. So multiple reactants, one product. So very bright exothermic reaction we saw when we did that. Now decomposition is pretty much the opposite of synthesis. It's one thing breaking up. So we have one reactant and multiple products are created. So generically, again, it's the opposite of the synthesis. AB breaks up into A plus B. Now don't get stuck thinking it has to be 2 things. You could have multiple. You could have 50 things, whatever, you know. But it's one reactant that you have to start with. So our reactant here is the fertilized egg. It's got everything inside there, right? And then it's hatching, and then once it hatches, we got the empty eggshell, and we have the turtle come out of it. Chemically, something we'll talk about here is breaking up of water through using electricity. So it is endothermic, takes energy in to break these up. And we can break oxygen, get oxygen and hydrogen gases out of that. Remember, oxygen and hydrogen are diatomic, so there's 2 of them there. But we'll do this in class, and you'll see that we get twice as much hydrogen out of it, because there is twice as much hydrogen per mole of that water, so it makes sense how it's going to do that. Now, something specific you should be writing down is with a carbonate. When carbonates go through decomposition, they'll break into an oxide and carbon dioxide. So what that means, here's an example. Calcium carbonate breaks into calcium oxide. That's the oxide part. A metallic oxide is another way of saying that. And carbon dioxide. So if I had potassium carbonate, it would break up into potassium oxide and carbon dioxide. So it's always going to be doing that with the carbonates. Single displacement, we have an element and a compound. And so there's one part that switches part of the group out. So as we think of our reactants are an element and a compound. And so we have somebody by themselves, A plus BC. BC is our compound. And then A switches out. A and B are both like metals in this case, and then they one replaces the other in the compound. So, looking at the picture here, we have Bob and Mary at the dance, and Joe is all dancing by himself. But, you know, now something happened, and now Joe and Mary are dancing together, and Bob's all boogieing by himself. So chemically, we can think of aluminum with copper 2 sulfate. We have an aqueous solution, so copper 2 sulfate is dissolved in water, and the aluminum is introduced as a solid, and we'll see a reaction. We'll do a lab like this, very similar. We'll use zinc instead of aluminum, but same idea here will happen. We'll get copper metal out of it, and then we'll get the aluminum sulfate in solution. So the copper and the aluminum have swapped. Also think about this: when it's copper 2 sulfate, that copper is an ion. That means it has a positive charge. It has lost electrons. The reality is that copper takes the electrons from the aluminum, and now the aluminum's the big loser in the formula here, and it's the positive ion, and copper is neutral now. So this is sped up a whole lot. So it doesn't happen this quickly, but we'll see it take place and look at it the next day and see that we are getting copper out of the solution. And notice how the blue is getting out of the solution there too, because we have the compound here. Oops, that killed my animation. There we go. And so we see the blue coming out because we don't have copper dissolved in the solution anymore. Now, there are limits with this single displacement reaction, and we need to look at this activity series. Move my down out of here. Maybe I'll move myself up here. Whoa. And we have this activity series, and you notice where copper is on the series, way down here, below hydrogen. Hydrogen is the only nonmetal that can work in with this metal group. But we see aluminum is way up higher. That means aluminum is more reactive, and the more reactive element is the one that's going to end up in the compound. So if we tried to replace this, like I wrote down here, if I took the end result of the products of this reaction and had copper and aluminum sulfate, nothing would happen, because the more reactive element, aluminum, is already in the compound, and we would not have a chemical reaction. This would just be a physical reaction going on. So when you look at these, you can't just always say, oh, it's going to happen. You have to look at this activity series, which is in the back of your book in Appendix A. I can't remember the page number, but you'll want that bookmarked because you'll be flipping to that a lot to make sure that the single element here is more reactive than the element in the compound, because the more reactive element will end up in the compound. So, okay. Double displacement. For this reaction to take place, we have two groups and their switching partners. So, as we think of two compounds, the ions of the same charge will switch. Like a metal will switch for a metal, or non-metal will switch for a non-metal, whatever. So AB plus CD equals CB plus AD. Notice how I kept the ones that were first, because just like our compounds, positive, negative, is going to stay that same pattern. So here we got the penguin with the hat and the pig with the glasses, and they switch parts around, right? Here's a chemical example. We have silver nitrate that's aqueous and sodium chloride that's aqueous, and now they're going to switch around. The sodium can get with the nitrate, +1, -1, look at the charges. Silver will get with the chloride, +1, -1 again. But this silver chloride we see is a solid. So it's not going to dissolve in water. We'll talk about rules for this, but things come together and they lock together. They hook together so well, water can't pull them apart, and that's when they're insoluble in water. And we'll have rules that we'll go through. You'll be able to identify which ones will do that. So here's what it looks like. We had two clear solutions, but when they combine, we get this solid silver chloride, which is a white precipitate is what we call this. The solid formed from two aqueous solutions is called the precipitate. All right? And we'll use a lab and identify things by their precipitates. if both products are aqueous, then nothing new is formed. When you mix this, it's like, oh, I put these two together and nothing happened. So you would say, yeah, there's no chemical reaction going on. It is just a physical reaction. Combustion is basically burning fuel. You know, we have gasoline internal combustion engines that we use in our cars. So the general form of it is some kind of fuel, whatever your fuel is, reacts with oxygen, and it always creates carbon dioxide and water. So here's an example of methane. It reacts with oxygen, O2, and then creates carbon dioxide and water. Now, I'll start balancing these and talk about, we can see everything here is working out on the same side. So this is a complete, or this is a balanced equation there. So as we look at another reaction with butane, I'll do this one also. We see it takes a lot more oxygen for this to happen. As we're putting these numbers out front, it's showing us how many of those molecules are being created. And so that's the balancing part. So to balance these equations, we have a law called conservation of mass, and mass cannot be created or destroyed during a chemical reaction. So whatever you start with has to be the same as what you end with. So just like doing laundry, you know, you go match up your socks. It's like, I'm missing a sock. Where did it go? It didn't just disappear. It really had to go somewhere, right? So things don't just disappear. They go somewhere. It's stuck in the washing machine, or cling to the back of your shirt or something, right? So those numbers that we put out front are called coefficients, and they show us how many of the molecules or atoms that we need to have to make it work. So we have the same number of atoms of oxygen or sodium or whatever on each side of the equation. So here's some examples. Let's get a nice blue pen here. So we talked about water. Let's make this a little thicker too. And we have, there we go, H2O, and we used electricity, and we broke this into hydrogen gas and oxygen gas. Now, as we look at the amounts and we think of, well, what is this really like? And just like as we talked about structurals, it's a bent molecule like this, but we have these diatomic molecules of hydrogen and oxygen. I'm not putting my valence electrons around there. But we start with 2 hydrogen, we end with 2 hydrogen. We start with 1 hydrogen and end with 1 oxygen, 2 oxygens here. And where'd that other oxygen come from? That's crazy, right? So that can't happen. So as we think of trying to balance this, what we can say is we're going to need 2 of these water molecules. So 2 of those water molecules, I would have 2 of the waters like this. And now I have 2 oxygen here and I have 2 oxygen over there. But I see that the hydrogen is not balanced. So I need to put a 2 out front of this, saying that I need 2 of those hydrogen molecules like that. So now 2 times 2 is 4. So I have 4 hydrogen here and I have 4 hydrogen there. I have 2 oxygen here and 2 oxygen there. We don't put a 1 in front of the oxygen. That 1 is implied. Okay, let's try another one. Let's do the other reaction we saw. Let's do a synthesis reaction with magnesium and oxygen gas. So again, as we look at a product, magnesium is a +2, oxygen is a -2. Don't worry about what they were like over here. We need to just think about what are they going to make, right? Because they're making something new. It's a chemical reaction. So to balance this one, I see that I'm starting with 1 magnesium, 1 magnesium. I have 2 oxygens. I need 2 oxygens here. So 2 of those magnesium oxides will use up my 2 oxygens. But to make 2 of those, I must have 2 magnesiums to start with. So now here's my balanced equation. I have two individual magnesium atoms. That's the difference between having it Mg2. That means that they're bonded together. This means two individuals or two of those molecules, right? This is the set, H2O. And this is just the way magnesium comes. It doesn't come in diatomic groupings like that. So there's our balancing for magnesium oxides creation. Oops, just want to wipe that. Okay, so let's do aluminum. Let's do our single displacement. Copper 2 sulfate. We made copper, metal, and aluminum, which is a +3. Sulfate is a -2. So it took 3 of those, build up +6 and -6, and that's how we get those to work. So we look, what's wrong here? Well, I got one copper. Now, when you do this, it's going to be to your advantage to think of this as one thing, right? I have sulfate there and I have sulfate there. So I have one sulfate here and I have 3 sulfates there. It's like, oh, well, that's a problem. So to make 3 sulfates, I better have 3 copper 2 sulfates. So 3 of those molecules. Well, to have 3 of those molecules, I must also have 3 coppers. And so I need to have 3 coppers on the end. When this breaks apart and we look at what we have left over, I'm going to have those 3 coppers. So to make this all come together, I need 2 aluminums, and I better start with 2 aluminums. So there's our balanced single displacement reaction. So let's do a double displacement. If we have the sodium phosphate, sodium phosphate, PO4, plus silver nitrate. This is a different one that I did on the examples of the reactions. So what's going to happen? We think of switching the metal for the metal, right? So we're going to get sodium nitrate and silver phosphate. Silver is a +1, phosphate is a -3. So, whoops, -3, but it's phosphate. So, there we go. +1, -1 for sodium and nitrate. So, again, think of phosphate as one thing, right? There's one phosphate here and one phosphate there. Well, I see trouble right away with silver. There's 3 silvers here, there's only 1 over there. So if I change this to a 3, that makes 3 silvers. But that also means by having 3 of this group, I have 3 nitrates. So 3 nitrates, over here I just have 1 nitrate. So I can't change how these combine. That's nature, +1, -1, but I can change how many we have. And so we're going to make 3 of these sodium nitrates. I'm going to need 3 sodiums to make that work, and hey, I got 3 sodiums over there. A lot of times that last one just kind of falls in place, and as you go through that chain effect, just like I'm doing here. I put this coefficient out there to fix this, but it also changed another part, and then you just kind of go back and forth like that, and it works out pretty well. So let's do one more. Let's do a combustion. We have butane that's in a lighter. It's going to react with oxygen gas, and that is going to create carbon dioxide and water vapor. It's hot. So we start off here. I got 4 carbons here. I better have 4 carbons over there. Well, I see oxygens in 2 spots at once. I'm not going to worry about that. I call that being split up. Save that to the end. It's a lot harder. So I'm going to worry about the oxygens last. I fixed the carbons. I have 10 hydrogens here. Well, to get 10 hydrogens, I'm going to have to make 5 molecules of water. Because every molecule of water has 2 hydrogens, so 5 times 2 is 10. So that's 10 hydrogens right there. Now, we look at our number of oxygens. So because of this, each one of these has 2 oxygens, so 4 of those makes 8 total. 5 water molecules is 5 oxygen, so 8 oxygen plus 5 oxygen is 13 total. So to get 13 out of this, it's like, what could I put out front to make 13? Well, mathematically, 6.5 would work, but we know that's not reality. Just like you can't go to the store and tear open a package of socks and bring one up to the counter. That's not how it comes. They won't sell it to you like that. Oxygen comes in pairs, so it has to be whole numbers here. Mathematically this works, but for chemistry we need to talk about whole number ratios. So, as we think about doing this, the trick here to fix this is to double everything. If I double this, now that means I have 2 of those molecules of butane, so that means 8 over here. I'm just going to erase everything here. You can think of those numbers that I had, but I'll just redo them. So now I need 8 here because I have 8. 2 times 4 is 8. I need 8 here. It's like there's a 1 there. 8 times 1 is 1. So 2 times 10 is 20. So 10 times 2 gives me 20 hydrogen. Again, I'm saving that oxygen for the last part. So now I look at my total. 8 times 2 is 16. 10 times 1 is 10. So that's 26 oxygens. So what do I need to put here? Well, it's double what it was. It was 6.5 before. Now it's 13. 13 times 2 is 26. So if you get to that point where you have like odd and even numbers on one side or the other and you can't get it making it work with whole numbers, double it, and that'll make the whole numbers come out of this. So you can do a lot more in your homework now. Do the balancing. We'll do some more practicing of doing these reactions in class. So go ahead and get to work.